We have a couple of other methods for evaluating limits, and right now they're just sort of some ad hoc methods. We'll have better ways of evaluating limits as we proceed in class. One way we have of evaluating limits is to relate a two-sided limit to the one-sided limits. And it turns out that a two-sided limit, the limit as x approaches c from both sides of f of x is equal to L precisely when the limit from the left is equal to L and the limit from the right is equal to L. That seems kind of intuitive. Well, where is this useful? This is useful when we have a function which is defined by two different equations on two different sides of a point. For example, the absolute value. Let's evaluate the limit as x approaches 0 of the absolute value function. Now this black line right here, this black V shape, represents the absolute value function. One way of writing down the absolute value function as a formula is to say that it's equal to x if x is greater than or equal to 0, and negative x is if x is less than 0. A lot of people don't like this. They say, but that means that the absolute value of x is negative when x is negative? No. If x is negative, putting a negative in front of it makes it positive. But maybe a better way of seeing that this formula is valid is to see this red line here is y is equal to x, this green line here is y is equal to negative x, and to the left of 0, the green line and the absolute value agree, whereas to the right of 0, the red line and the absolute value agree. Okay, so this formula is valid. So, to evaluate the limit as x approaches 0 of the absolute value of x, we can replace the absolute value with one or the other of these equations, these expressions, depending on which way we're approaching 0. So first of all, if we approach 0 from the left, the absolute value is, then x is taking on negative values. So the absolute value is equal to negative x. So we can replace the absolute value of x with negative x, and then we can just plug in 0. All of our limit laws hold for one-sided limits. So the limit as x goes to 0 from the left of negative x is negative 0, which is the same as 0. From the right, x is positive. That means that the absolute value of x is just given by x. So when we take the limit from the right, we can replace x, the absolute value of x, with just x. Then the limit as x approaches 0 from the right of x is 0. So since both one-sided limits exist and are the same, we can conclude that the two-sided limit, the limit as x approaches 0 of the absolute value of x, is also equal to 0. We can also use one-sided limits to show that a two-sided limit does not exist. One example where this happens is something called the greatest integer function, which we write by these sort of double square brackets around x. You can look in the book or on the internet to find out what exactly the greatest integer function means, but what I care about most is what its graph looks like. It is often called a step function or a stair function because the graph goes up sort of like a staircase. Okay, let's notice that it's basically constant, except at every whole number it jumps up by 1. And so at 0 it's equal to 0, and then it's equal to 0 until we get to 1 where it's equal to 1, then it's equal to 1 until we get to 2 where it jumps up to 2, etc. So let's evaluate the limit as x approaches 2 of the greatest integer function. Well, we don't have a single equation for this, but we can evaluate this from the left and from the right. From the left, what happens as x approaches 2? Well, as x approaches 2 and from the left but is close to 2, the value of the greatest integer function is constant and equal to 1. So as I approach 2 from the left, I can replace the greatest integer function with 1. And then the limit of a constant is that constant, so it's 1. From the right, as I get closer and closer to 2, as x gets closer and closer to 2, the y value is constant equal to 2. So as I approach 2 from the right, the greatest integer function is just equal to 2, and the limit of a constant is 2. So the one-sided limits both exist, but one of them is 1, and the other of them is 2. Those are not the same number. If they're the same number, I'm out of a job, probably. So, no. Great. They're not the same. The limit as x approaches 2 of the greatest integer function simply does not exist. Another useful fact about limits we have is that if f is less than or equal to g, close to c, but maybe not at c, then the limit as x approaches c of f of x is less than or equal to the limit as x approaches c of g of x. If I apply this to three functions, f g and h in order like this, then I get something called the squeeze function. So suppose for x close to c, f is less than or equal to g, and g is less than or equal to h, and also suppose that the limit as x approaches c of f is equal to the limit as x approaches c of h of x, which is some number L. That means we're in this sort of picture right here. F is the bottom function, g is the middle function, and h is the top function, and I'm saying that as x gets closer and closer to c, h and f both approach L. Well, if that happens, then look, g is stuck between the two of them, and as we get closer and closer to c, g has no place to go except for L2. It's going to stay between h and f. So if the limits at c of f and h are equal to L, then the limit at g has to be at c of g of x has to be equal to L2. The way we typically use this is that g is some sort of weird function that we can't apply our typical limit laws to, but f of x and h of x are sort of nicer functions that we cook up that saddle g in a manner like this. That f and h are functions whose limits we can compute easily at c, and then we can figure out what's happening at g too. So here's what I would consider to be sort of the prototypical squeeze theorem example. Let's evaluate the limit as x approaches 0 of x squared times sine of pi over x. Now I can't plug in 0 into sine of pi over x because I'd be dividing by 0. Also, I can't break this up into a product of limits. I can't take the limit of x squared as x goes to 0 times the limit as x goes to 0 of sine of pi over x, because we have already seen that this second limit right here does not exist. That's where the function was oscillating infinitely often between -1 and 1 as we approach 0. However, this function, sine of pi over x, is pretty well behaved for a badly behaved function. Namely, the values of sine are always between -1 and 1, so long as x is not equal to 0. Okay, well let's take this expression and multiply it by x squared. What do we get? Negative x squared is less than or equal to x squared times sine of pi over x, which is less than or equal to x squared. This is good. These are the three functions in a row. Negative x squared and x squared are playing the role of f and h. They are well-behaved functions, and I can evaluate their limits at 0 because they're just polynomials. Now the limit as x approaches 0 of negative x squared and x squared are both equal to 0. They're polynomials. I can just plug in 0. Therefore, by the squeeze theorem, the limit as x approaches 0 of x squared times sine of pi over x is equal to 0.